So you so this session we are going to see some transaction happening in real time, and we'll look deeper into how transactions look like, how interactions amongst what happens in the blocks and so on. So let's look into, we just had this recap on the consensus from the last part, and we also saw the application of IoT using blockchains. So in this lecture we will really understand what transactions are, because ultimately if you are looking into blockchains, and these are things we'll do during the rest of the week. We'll look into how you can build your own application on blockchain. So we'll try to understand what blockchain transactions look like. Okay, so we have done this before. Just a reminder that we want to transfer something from Alice to Bob, and we want to create transactions, group transactions in the blockchain. This is something that we have seen so far. Okay, and we have also seen that it is broadcasted in the network, blocks are verified, there's some consensus going on, and after that blocks are added to the blockchain. Yep, this is all done. So we did say that, there's a wallet. Alice has a wallet. It has many, it can have many accounts. Bob, on the other hand, has a wallet B, which can have many accounts. And very naively, a transaction would look like a transaction from Alice to Bob. So these are things that she has to show that she has enough money and she has authority to spend it. And we will see how transactions look like in real practice. So before we get started looking into the real data, a couple of things to keep in mind is how we store models of storing state information in blockchain, because state is something that is changing every time a block is added. So think of the state as to be constantly changing when blocks are added, and how we store the state information is something to really understand. Because if even in the previous lecture you saw that the scalability is a big issue. So you are storing a lot of data about the blockchain itself. So understanding how to properly organize the data so that you can efficiently retrieve it later is something to understand. So there are a couple of, most importantly, there are two models for storing data. The first one is called the UTXO, or the unspent transactions output, unspent transaction outputs. So it will be outputs actually, unspent transaction outputs. So think of your wallet, simple wallet. What do? You keep your money in the wallet. So now if someone asks for, say, 25 rupees, what would you do? What would you do? You will take out some money and pay it, right? Now, do you have a $25 bill? No. What will you do?
120 or give 50 rupees.
Yeah.
30 rupees.
Yeah, exactly. So you can do it in many ways. So if you have a $50 bill, a 50 rupees bill, you will give it to the person and they will get back you 25, 20 plus 5 maybe. Or you can give 20 plus 5 if you have it in the wallet, right? So essentially, this is the model that is followed in the UTXO. Whenever think of UTXO as a wallet, it is not just your wallet, it's everyone's wallet all over the world, or everyone that Bitcoin is maintaining. And these are all unspent transactions or unspent transaction outputs, which means that all the bills that you have in all your wallets together. But I can use bills from my wallet only. But my wallet will consist of all the bills that I have. If there is an unspent thing, like say for example $50, 50 rupees, I'll get back 20 plus 5 in my wallet. And that is exactly what UTXO does. So you have a list of transactions. When you give someone, say for example, you are moving, you're giving something to, we'll start writing things now. So think that you have, say, Alice and Bob. So Alice is giving, so this is say $50, and then she gives Bob, so this is 50, so Bob gives 50, Alice gets 25 back. Think of this as an input to this transaction, and this is output of the transaction, $50 to Bob and $25 back to Alice, right? This is what typically happens. This is how our normal transactions work, and this is exactly how the UTXO works. So essentially what you would have in the UTXO is that all these unspent transactions, so this becomes now Alice's unspent transaction. So similarly you will have another bill in your wallet. So this is added to your UTXO. So this UTXO essentially, whenever you want to spend something, you have to choose something from this, whatever you have in the wallet. So now you have 25. So in the case of Bitcoin, you can have any dimension, right? In normal currency, you would have only a few types of notes. Now in this case, you will have 25. Now if someone is asking for 30, you could give 25 plus 5, right? So this is how UTXO model works. It's very similar to our wallets. And Bitcoin, Cardano, they use this UTXO model. However, Ethereum works in a different way. Ethereum has an account-based model, and account essentially is account address. So every person, say within a wallet, think of this as a wallet, they can have multiple accounts. So this is account, this is Alice's wallet for Alice, and this is like account A1, account A2, and so on, right? So now in Ethereum there are two types of accounts, an externally owned account and a contract account. Externally owned account would be like accounts that are where you can make transactions from one account to the other. In the case of a contract account, every smart contract, corresponding to every smart contract, you have an account, and if the values of the smart contract would be stored in this contract account. We'll see these later. So first we will look into the Bitcoin, and then we will go and check how Ethereum works. Now, if you think of the UTXO, UTXO is a big list, and everyone's wallets have all this list of unspent transactions. So it's a big list. Whenever you want to spend something, you have to have some algorithm to choose which one to use next, and there are different algorithms that different wallet service providers might be providing. It's much like the money in our pocket. Okay. The next thing that I wanted to say is that I'm talking about account and account addresses. So in Bitcoin, it is essentially the Bitcoin account address is something of this sort, that for every account you have a public key and a secret key. This we have talked before. Now this Bitcoin address, or say account, with every account you have an address. So wallets, account, and this is address of the account. Address of account 1, address account 2. Actually there's more fields to this, we will talk about this, but all this is like, account A1 has an address A1, account A2 has address A2, and so on. And these also have secret keys and public keys. So you have SK1, PK1, SK2, PK2, and so on. And the way Bitcoin address is is derived is by using this function. So here, this public key is a public key of the particular account, and then you use SHA-256, I ripened 160. So these are all known functions that are applied to this public key to get the Bitcoin address. Secret key is not known to anyone. Now, this is for your information. Now, next, what we will look at is this thing, and then we will see how things are working in real when I will talk about this particular aspect. So, what we have to do essentially is that I have a public key and I have a secret key associated with my address. So, when I want to spend something, when I want to make a transaction, I have to sign. I have to sign and say, look, I'm signing with my private key, meaning that I have this amount of money and I'm saying that, okay, I'm opening this or I'm signing it with my private key, and I'm sending my public key along so that when the money is being spent, everyone will verify with what I've with the signatures that was on the transaction. So let us look. I mean, if I say this, it will not be very clear to you. So let us look into some of the accounts and see how the structure looks like and what is exactly done. Okay. So I'll do one thing. So this is can you see clearly? Yes.
Why are we hashing the public key?
Why are we hashing the public key?
Yes. It's a public data, right? So
Yeah. So
not very large, right?
no.
If I am using digital man or electric copies.
Yeah. No, this is just, everything is public here. It is just a way, because you have the public, you just want a very fixed length size.
Right.
To apply the ripened 160, and that's what is being done for this this Bitcoin. So there's no other reason why you are using this hash function. Is not used for any specific purpose. Other than that, you really want a yeah, exactly. And you also need that randomness.
Right.
Okay. So this is, can you see? This is actually, I can't remove this part, but okay, we'll see. So this is actually this bitcoin.com. This gives us a list of, all that is happening in most of the known crypto currencies, and you will see Ethereum, Bitcoin, everything here, and all the data that you were looking for. You were asking me in the morning. You will get a good idea of what exactly is what. So Bitcoin, for example, you will get real-time information about the prices for Bitcoin, Ethereum, Ripple, and so on. So this is a place where you have all sorts of information available. Now let us look into these transactions. Are you seeing these transactions here? You see? So this is happening in real time. So these are Bitcoin transactions happening in real time. So it tells you how much these transactions are worth, and say for example in BTC, and they're also giving it in dollars, US dollars. And on the other hand, on this side is some number that you can see. It's not very clear. I mean, I don't know how to remove this thing, this crypto wallet from the middle.
Just zoom out the screen.
Yeah, I can do that, definitely. Okay, now let's see. See that this is your the prices on the right hand side, the latest blocks that are created for Bitcoin, and then you would also see, the yeah. Oh no. Yeah. So you would see that these are the latest blocks, the latest transactions. You would see the latest transactions happening. So these are the transaction hash. So it's just an ID of the transaction, and all these IDs are actually hash values. It will tell you the time at which it's taking place, and then you have, my clock, my machine's clock is set to my Australian time. That's why you are seeing 21:12, and you will see that this is happening in real time. So the 0 essentially means that it's very, very negligible amount of Bitcoin. So it's like that's the value that's there. Okay, so this is something that's happening. Let us do one thing. Let us look into a little bit closer at each of these things and see how these blocks work. So I will choose, okay, Ethereum. Okay, there's also a little bit more information about Ethereum. It tells you the transactions per second. You will see that there are transactions per second. These are transactions per second. Then the number of blocks. This is actually the block height, current block height. So how many blocks are totally there in the Bitcoin? Sent today, how much worth of Bitcoin, US dollars have been sent today? How many, the network hash rate, and then the unique addresses that have been encountered in the last 24 hours. So these are, and the blockchain size. You will see that the blockchain size is also given here, 648 gigs. So this essentially, all the questions that you were answering, how big things are, how frequent are my transactions, everything, that information you will get from here. So now let us look a little bit closer into this Bitcoin. So here you will see the price fluctuation in Bitcoin. And the most interesting thing over here is this blockchain. So these are all blocks in the Bitcoin. Yes, question.
Can we use this data? If I want to download this data,
Yeah.
because all the data is public, and I want to do experiment with this data, so how can I download?
Yeah, so there's already, this all this data exists as JSON. So you have to use a suitable AI to download all your the data using, all this JSON data into your.
I have to Google it.
Yeah, just Google it. Yeah.
Okay, so will it give me the latency between the blocks and
Everything, all information. You'll get all information. All is with public.
I'm going to share that AI with us.
API.
Yeah, how to communicate with the server.
Blockchain.com also has the API. This website.
This website would have. You have to search somewhere. It will be somewhere in
It's not providing
maybe.
the whole information, ma'am. It's providing the recent information only. I've worked with it, but it's not providing when the block is created, because all these things are public. But we were not able to.
Oh, okay. So that's an interesting question that I think it's very important to note. In all these, what are these websites doing? This blockchain.com, all these are doing. They are simply, displaying this information, right? So most of this, you will see that they don't essentially have a lot of historical data, right? So I'm not too sure about the Bitcoin archival data, but there are implementation, for example, Geth implementation for Ethereum that essentially gives you all the historical data.
If you want entire
No?
data, you can
No,
just
ma'am,
download.
it's not. It's also not providing you. It's only Geth is also providing the current information of the blocks.
Okay.
But if you want like last 1 year data and last 2 year data to find out whatever we are implementing to remove that latency and the like block size. If I am working on block size, I want to reduce the block size, and that information where from we can get it.
If you need that much data, I guess you can just run a node till where
Yeah, that's the way.
a node can sync till
Yeah.
where you want.
Yeah, that you can do. Yeah.
That will
Yeah, that will be, yeah, that you have to do, yeah.
Pretty sure there would be some API, I guess.
Yeah, there would be some API to do that. I mean, and I cannot tell you over the top of my head, but these websites, they will give only for, you know, a period of time.
Current information they are providing.
Yeah. Even if you think of Ethereum stores the information of last 122, 128 blocks.
We are unable to download it, ma'am. Even 128 block data will be enough for the research.
Right.
purposes.
Yeah.
It's not. We are not able to download it. We can see that how many blocks have been generated, but we are not able to watch the.
Yeah, so you have to have a, you know, node running. Yeah. Any more questions? But these are very interesting questions, because if you are developing something, this is something, you know, you will be looking at. Okay, so this is, say for example, the blocks that you are seeing these blocks, and the block height is also visible here. And this is all the information that you can see over here. If you scroll down, you would see the transaction and all the blocks that were there. So whenever you want to get some information about the blocks, say for example, you need, so this is a little bit earlier during the day when I was just checking things up. You would see that this is a block number. This is a hash of the block. You will see that the miner who has mined this block, and here, can you see from the back? Yeah, okay. And in the morning we saw, you know, we saw the mining pools. So for example, here some of them are unknown, but some of them belong to some mining pools. So you would see who has mined this block at what time, and then you would see the number of transactions. So yesterday there was a question, how many transactions per block, and it could vary. So you see that there are 1600 transactions, but then there are again 2700 transactions, more than 2700 transactions. So this number of transactions can vary. So the size of a Bitcoin block should be less than 4 MB. Okay, and then this is a nonce value that I was talking in the morning. You'll see that, as I said, you have to change the nonce so such that, you know, you are able to solve the puzzle. So this is a nonce value. Then the size of the block, the total spent, and the total fees. So fees also, if you remember, we talked about transaction fees, and we were saying that for every transaction that's happening, you have to pay a transaction fee to the miner. So this is the sum, that's the total transaction fees from all the transactions in the block. So, you know, just playing with this sort of things can help you learn more about how exactly these blockchains, these blocks look like, how transactions look like, and so on. So let us.
What is the fill percentage?
What is the fill percentage? I'm not sure about that. Fill percentage, I think, would be, because it's 154.66, right? I'm not too sure, but it just gives an indication of, you know, how much, you know, because there are a few where there are very few transactions and this fill is low. So it is like the density is something like a density of the block, some measure, but how exactly it is calculated, I'm not too sure. Maybe this is question that you can tell me tomorrow after looking up. Okay, questions anyone at this point? Okay, so now let us look into a block. So let's see what the block looks like. So I was looking at this block. this. Say for example, we are looking at this particular block. Look at this information that's already there. Let me just, so all that we were talking about today, all the details of the block are available here. And what this is Coinbase. So the Coinbase is essentially, this is essentially, this information is given by Coinbase. So Coinbase is again, it is one of the, it does many things, including it has also an exchange as well. Now what they are saying is that a total of, you know, so many 7,000 something BTC are found within this block with an average transaction of so much. So you'll get all this information here. So let us look what this block consists of. So the hash, every block has an ID, and this is a hash of the block. So it will take all the information in the block and hash it together. The capacity is something that I'm not too sure about. So let us, you know, defer it for tomorrow. Distance. Yeah, so distance means from now to this place, this time, when was a block created? So it was created 14 hours, 55 minutes. So how much value, total BTC? How much of it is in the US dollar, value today? So all these information essentially tells you a little bit more about the value, median value, input value, and so on. Witness transactions. So this is essentially related to you know, the Bitcoin scripts. So in the morning I said that you want to verify a transaction, right? So this essentially is run using a Bitcoin script. Bitcoin script is nothing but a, you know, a logic just to check the validity of a transaction. And this witness, SegWit, was proposed to which essentially a way, so the number of SegWit transactions per block. If you just put the cursor here, you will see that it's written the number of SegWit transactions per blocks. So earlier, the SegWit came around, I think 2018 or so. Before that, a SegWit essentially helps to reduce the size of the block. Now, before that, there were no SegWit transactions, and they had a different set of scripts. I'll show what the scripts are. There's a lot of scripts. So essentially, you know, it's a piece of code. It's very little piece of code. The transactions, the inputs, outputs, so many inputs, so many outputs, fees, total fees. So there are all these things, the depth from now till then, till the block. Okay, then size, total size of this block, the version, the Merkle root, we all know about these things. The difficulty, we talked about this in the morning. So the difficulty is kept, the nonce is kept, the number of bits. Weight, I'm not too sure. The reward, so you see the reward, there's a reward associated with this block. It is 3.13 and it is mined. Okay. Reward. Then there are other things like confirmations is essentially how many blocks have been created over and above this block. The number of confirmations says from when this block was made. So for example, you have this block here, but then after that there were many other blocks. So there were 86 other blocks that were created on top of this block. That says like it's confirmed. In Bitcoin, we need 6 confirmations to keep that block. Before 6, you can still remove it from the chain. Then there are other things that you can see, average fees, median fees, and so on. The miner, we are not sure who the miner is. Because some miners, some of them you know their address, some of them you know the pool, name of the pool, but then some are anonymous. Yes.
Let's
have a very basic question, and I might be stupid, but when Bitcoin actually started, the Genesis block created.
Right.
So how it created some value, like to donate? It's very famous that he bought the pizza from some pizza store, and the pizza store gave him pizza, and he transferred his Bitcoin to him. So you might have listened to that story.
Yeah, so what was the question? Sorry.
The question is how he mined the values. Like if I start earning, then I might come to you and you are going to pay something to me. Then how on Bitcoin those value generated?
Okay, so in the morning we were discussing this, like the Bitcoin, some Bitcoin is minted. So when the Genesis block was created, the Bitcoin was minted. Means you are printing currencies, something of that sort, equivalent to this. So it never existed.
Yeah.
Now you're printing something.
Okay.
So all of this is fully electronic, right? So essentially you are assigning a value to start with.
So after 2 or 3 systems are connected, they started like generating. How that money? So they were printing that money.
No, I'm saying that equivalent. No, there's no money. There's no nothing. It is something like I'm assigning. So in a code, if you think of this, everything is a code, right? Piece of code. So you set it from the, you set it. Say for example, you might say like value, the account value of the account address in the Genesis block is equal to 25.
Okay, I myself
50.
generated
Yes.
something, and I.
Yes, that was the first one. So first, the transaction in the first block. That is how.
When multiple systems are connected to it, it's going to.
Yeah, then everything is broadcasted, everything works in that way. But somewhere it started, right? Even this one, this reward that you are generating, you are creating this reward. This is essentially just adding some value from nowhere. It's not a transaction.
Then why someone is paying like for this much amount of money with 1 Bitcoin is something 5,000, 7,000?
Yeah, who told that number? What was that number?
21 million.
21 million, yes. So that number, so the Bitcoin essentially has a target of that 21 million, that that's the amount that we will support. Until then, they will keep on mining. Yeah, it's something of the sort, why this 21, I have no clue. I mean, this I cannot say. But think of it like, for us, think of normal, the any currency, every time you are printing new currency, and there's a flow of money in the market, right? So that is done by the government. It's something of that sort.
And when suppose in morning you were telling about that some node is selected as a leader. And suppose if I am having 10,000 Bitcoins and I am selected as a miner, but I don't want to do mining. Means I don't want to provide my resources. That's the mining, then what will happen?
Okay, so the first coin, the Bitcoin mining works in a different way. That the leader election and that one, that's not the protocol for Bitcoin.
Okay.
So okay, so there are a couple of things. So only nodes who want to participate will be selected. So for example, at the time of selection, if a node is sleeping or if it is defective, then it's not going to be selected. The reason being that only the active ones will be able to participate, because they have staked, right? If you have staked, then it is in your own interest that you will participate, right? Yes.
Here it is written that the reward was given 3.136 bitcoins, and it was mint. 3.13 bitcoins were minted also.
Yeah.
So that means the amount of reward that we are giving, we are minting that again into the economy.
Yeah. That's minted. That's new thing. Yeah. Good point. Any more questions here? Yeah.
In the process, the Bitcoin value was down. The minted means increase the Bitcoin amount, but price will be decreased.
Yeah. So honestly, I really don't understand how this prices work, I don't know. Honestly, I cannot say, how these prices, are determined for Bitcoin. Yeah, it is true that, but this is also anticipated. Everyone can anticipate that, because the blocks are coming at regular intervals, almost regular. You can anticipate that this much inflow will be there. And the price that is decided, or price that is there at this point of time, that is actually calculated taking all these factors into account. Factors in what formula? I don't know.
It is not like a stock market, right? Your stocks are increasing because the company is manufacturing a lot of things, but here things are different.
Yeah, exactly. And there could be multiple parameters, multiple factors on which these would be dependent. So, for example, you are asking a question that I am saying I can't answer.
There's been a specific price for it. Like who's behind that?
The market. The market.
I who found the Bitcoin.
No.
It's a demand and supply.
Yeah, this demand and supply.
And use and Bitcoin is good. Everybody started using Bitcoin and then
Yeah. Yeah. So, for example, when Trump won the election and he was saying about, he's a big supporter of, this cryptocurrencies and blockchain technology. So prices went up. So that's what I'm saying. Like, there are many factors in the market. But don't ask me how, please. But maybe this could be an exercise for you. So this is an exercise. Okay. So Friday we will have a session where we would be discussing all this. And I think there were a couple of interesting questions. One is this, the price, how it is determined and everything, that one question. And there was one more. Did you ask?
And where in the multiple tree, how can we detect which transaction is faulty in the multiple tree?
Yeah.
Because we only know the hash value of the multiple root.
Oh, okay. Which one? Okay, which one? There could be ways. Yeah, which one? Okay, that's another question. Okay, so we'll keep on collecting all these questions that we can't find quick answer in the class, and let's discuss this on Friday. Okay. So, okay. Now look at these transactions. Okay, these are the transactions. Okay, now next. And who wanted to have the start the Bitcoin mining? That would also be interesting. I want some thoughts on that as well. That would be nice to have, right? And you can come and tell me whether you finally decided to be a miner.
If you say how to start, you start.
Okay. Okay. Let's look at this. Let's look at the transactions. So you will see. Now I need some attention, please, class. Okay. So if you want to discuss a few things, maybe the right time is after my class, or you can go out and discuss. Okay, now look at the transactions. If you would see that every transaction would have an ID and when it was done. So you would have a timestamp here. It's not quite visible. So let me just, yeah. So you would see that all these transactions have this IDs and that when it was mined. Yeah, so this was, so for example, this one, for example, it has two inputs, from two inputs and to this particular address. So let's look into one of these transactions. Okay, so look at this transaction. So this is a hash of the transaction or the hash ID. the amount of transaction is 0.029 BTC. The fee is, this is Satoshi, this is called Satoshi, SAT. And then there's this value that is associated in dollars. So this is a transaction fee that you are paying, and this is from 2 input to this particular one, and this is a transaction that has been confirmed. So as I mentioned, there could be some forks, and that some of the transactions might be, some of the blocks would be discarded. So that's what we wait for 6 blocks after the block, you wait for 6 blocks to get enough confirmation to make this a permanent one. Okay. Now, that's why, to get a confirmation, you have to wait for 1 hour. Each block is generated around 6 every 10 minutes. And for 6 blocks, you need at least 1 hour to get a transaction fully confirmed within a block. Okay. Now, if you look in the summary of the transaction, look at this. You see that, yes.
Now you say it takes time, almost 1 hour for all transactions to get confirmed. So for that period, the transaction is not debited. Is it in a transaction?
It's not, I would not say. So whether it's debited or not, yeah, so if it is not, I mean, if it is dropped, then the transaction again gets, it does not take place. So you can think of it as like a pending transaction.
Transactions are confirmed, but it's just a good practice to wait because of the fork issue.
Yeah.
Like sometimes what happened, like they split up, the chain split up at some transaction.
Yeah, so we have seen that, the forking strategy in the morning.
It's a good practice.
If the money is received,
Yeah.
you can
The money could be received because which node you are referring to, whatever wallet your node is referring to, shows that the money is received. Doesn't mean that's the longest chain. Maybe that chain the second chain is selected as the final chain. It's the longer chain. Maybe after some time. That is why you need to wait 1 hour.
Thank you. Okay, so this is a hash. This is the position. So it is the the transaction. We had a list of transactions. This is the 9th transaction. Age means from now till when it was mined, when it was made, when this transaction was made. Input value, the fees, transaction fees, and weight. I'm not sure about the weight. Was it a coin-based transaction? No. So Coinbase essentially means that sometimes this Coinbase transaction is a transaction where when you are minting it, so that is a Coinbase transaction, and then there are version numbers associated with these inputs and outputs. This is something to keep into mind. So you will see that there are 2 inputs, 1 output. So of this form, there are like 2 inputs and 1 output, meaning that I have $20 and $5 and I'm giving you $25, something of this sort. Okay. Next, you have the output value, the fee per block, so on. Witness, yes. Is it a witness transaction? So as I said, that SegWit was not in the original type of scripts that that Bitcoin had. So these were included later, and it says that it is a SegWit transaction. BTC price, lock time. Lock time is again, the block. So this is 890, 893, and this we are looking. So it is like all the blocks that has been there previous to this block. So this is, look at this. Now you will see this overview. Now if you click on the JSON, this is where you will see details about the transaction. So you see that there is a transaction ID, the size, version number, lock time, and everything that you saw in the beginning. But look at this particular thing. This transaction has the input. So this transaction is an input. This is an input. There are two inputs. So you will see that there are two inputs. This is the first input. Starts here. This is a first input. And this is a second input. And here you will see the output. So the first thing is that the address. So it is the input address. So essentially this is the input, this is the output. So for example, you could say that, you know, this is from this wallet 20 wallet address, which is, you know, BC1, etc. And this is from the wallet address, sorry, not wallet address, account address. This is an account address which is BC1, Q84, etc. And then this is also, you know, BC1, QXM something. So you would see that these are two account addresses in the input, one account address in the output. So this is an account address, output account address. So this is the output account address. Next, you would see the most important thing over here is this witness. This is a piece of code. I'm showing this in a bit. And then you will see the public key associated. It is not just a public key, it is a hash of the public key that is associated with this particular input. And similarly, you would see that there is a public key associated here and there is a witness associated. So what does this mean? Let us have a look. So I have it in my, I've taken a, put this in a slide. I'll show you how it looks like. Let me, this, yeah. So this is two input, one output. Now, you would see the witness. You would see the witness and you would see the public key script. Okay, so this is a public key hash. Are you observing it? It's very small. I don't know how to make it big. Maybe I should do this. Yeah, so look at it. This is a witness. This is a witness. This is a witness. This is the public key hash. This is a public key hash. And this is a script essentially that you want to run. So this is P2. This is called the witness, public key to hash. Witness public key to hash. So this is a particular type of script or a piece of code, you can say. I'm going to show you a list of codes that are valid codes that are executed when you look into such transactions. So you can think of this, our equivalent would be just, I'm doing some operations. This is the thing. The Bitcoin script is very narrow, I would not say narrow, I would say very limited in scope. It is not Turing complete. So you cannot essentially write loops and so on with this type of scripts. So what this script does, it does this: duplicate, dup, hash 160. It hashes it. Then it takes a public key hash. So this PK script is a PK script value that you have got there. It will equal and then it will check with the signature. So witness, if you look into the witness, so let us see what this looks like. If you look into the witness, it consists of two things. Actually, so there's a signature and then there's a public key. So you will see that there is a comma here. I don't know if you can see, there's a comma. So this is the signature and this is a public key. Okay, this is within the witness. So what you do when you run the script is as follows. Okay, let me show this. So you would have dupe 160 hash 160. This is public key hash, and then equal and check signature. Now what you will do, think of it as this. This is your signature, signature. This is from the SIGWIT, okay? The witness, witness. Signature and the hash, signature and the public key. So this is in the witness. As I said, there's comma over here. So the first one is the signature, next one is the public key. And then what you would be doing, and then you have all this, the public key hash. So you have so this one is a part of your witness. And also you have the public key hash, PK script or something. Yeah, this PK script, that is your public key hash. Okay? What you will do, or I would like just write hash of the public key this way. So what will you do? Dupe. Dupe means duplicate. So essentially what will you put on the stack? You would put the key again, dupe. You're duplicating. You're popping, taking the first value, which is the public key. You are duplicating it. So this is the public key. Then you pop and take the hash of the public key. So now this is gone. You are putting the hash of the public key. So hash of public key. So you are putting this here. Then you have this public key hash over here. You are checking if these two are equal. So you are popping it again, checking this if these two are equal. Okay, so if it is equal, let me check. I think this should not be equal. So you're checking with this and this are equal. Oh, wait a minute. I think I made a mistake. Yes.
What does dupe mean?
Dupe means duplicate.
Where is this duplicate? The word where does it fit in this context?
So I'm popping the stack. I'm duplicating the value on the stack.
Why we are doing it?
That's how you run the program. So small code. So this is done to verify that you have the correct signature. Huh?
Correct witness, yeah.
Yeah, you have the correct witness value.
Basically,
So
we are
we'll do this
maintaining.
in programming now. Where will we do this?
No, you have to check that signature. So for that you require a script, and that's what Madam is
Yeah.
saying. Equal check sig. Ultimately,
Where we are not doing anything.
No.
So this is a transaction that is being executed. We are not doing. The client is doing. The client is doing, and that's why all this information is required. So essentially what it will do, I think I made a mistake over here, but it should be popping the value or the public key, checking with the hash that you have got, and then you will check the signature. Check sig.
But
Wait a minute,
signature also
equal.
require the public key as input, right?
Which one?
Public key will be required to verify the signature, right? As an input.
Yeah. Oh, okay. So this public key is used to verify the check sig. Yeah, you are right. So these two will be used to verify whether this public key can check the, public key can be used to check the signature. But the good thing is that what you want is that your public key, this script, public key script, or the public key hash of the public key should match whatever you have got. So this is how the witness, how the script typically works.
Excuse me, ma'am.
Yeah.
And I wanted to confirm one. For example, Alice is sending a transaction. So first of all, she will encrypt the thing with a private key using the digital signature. Then she
No, there is no encryption here.
But what is the signature then? We are having some digital
No,
signature.
signature is not encryption. Signature is to sign, meaning that I am Alice, I am sending it.
So there is no digital signature. Visa, ECDC, TSA is not that.
Yeah.
It is that
Yeah.
So it is encryption only, right?
No. Okay, good question. Okay, this is very important. If you have anything to take back from this workshop, signature, authentication and encryption is not the same. So essentially your encryption is when you want to protect the confidentiality. If you talk, I will not be able to concentrate. Hello. So encryption is to protect the confidentiality of the information. Okay, and authentication is to say that, okay, this authenticate that the information is coming from the correct source. These are very different. So encryption, you want to protect the confidentiality. There you are using this different techniques, say RSA or maybe elliptic curve encryption algorithm. Again, on the other side, you could actually you could have, you could think of signature. Signature is, as I showed yesterday, signature is to say that, okay, I am signing means I have the secret key, I am the right person who can, who is a valid person to send this message or sign this message. Now, there you can use the CCDSA, but not encryption. Encryption is different. Encryption, we don't encrypt anything here. All this. What?
How to differentiate signatures? Like we are not encrypting it.
Yeah.
So we are saying digital signatures or what? Like,
digital signatures are signatures. Okay. What are it's not encryption. So essentially, in a signature, your message is there, your signature is there. Message is in the clear. There's no encryption. You see? There's no encryption. Encryption is when the message is garbled to something else. So signature is something of this sort, like the signature on this message. You need both to verify.
signature is something like private key?
No, so it is an output of a function. So if you have a signature, yes, these are, no, I mean, you should actually clarify these things because these are very important. So when you are saying that I'm signing a message, some message with a, yeah, it's the output of the signature algorithm.
Okay. It's like encoding?
It's some kind of encoding, yeah.
And so basically we have a message and we are applying a private key to give out a signature and connection to get a message, and then we can verify it using the public key of that sender.
Yeah, so the thing is that the signer alone has the signature, so alone it can authorize, it is an authorized to sign it, or if the someone else cannot sign on its behalf because it does not have the secret key. So that's the main idea, that no one else can sign it because they will not have my secret key, only I will have my secret key, so I can sign.
What is the difference between the witness and the signature?
Okay, so this witness, okay, I'll show you something. This is better. Yeah, so let me show you. I have just, okay. Not this. Let me show you this scripts. I'll come to witness. But blockchain, if you look into blockchain, you will see that there are many wait a minute, let me go to these are opcodes. Yeah, so scripts. I think you should have a look into this, because so this is how a Bitcoin script looks like. It's a piece of code, very small, but it's a piece of code. And just like we have, normal stuff, you can see that there are also different types of opcodes. There are some, these functions. You can do some logical operations. You can use some stack information, and so on. And these are the examples of script. So pay to pub skip hash, this is one. These are again obsolete. This is not for the witness one, but these were earlier used, and in also now as well. You will see here that there are certain opcodes which are used to signify different things. So for example, op push data, if it off push data, it will have this value 76. 76 is off push value. What we were doing is dupe hash 160 something. So let us look into the segwit and see what is dupe. Then you will see that, let me see if it is here. Dupe. Okay. So the best way to do is look into the segwit opcodes. Yeah, so for example, if you look into this particular script, you would see that where is that opcode gone? Split. Yeah, stack item. So 02 is that opcode of dupe. Wait, let me find it somewhere else. Segwit witness. It's an operation. Operator. Yeah. Why we are doing it?
Why we are applying and where are you applying this?
Yeah. So essentially, to validate this transaction. To validate the transaction. So to validate the transaction, you have to. So for example, if you are validating the transaction, you have to write a piece of code to check the signature and the message is correct, right? It's a verification algorithm, for example.
So to check, right, if the nonce is correct.
Yeah, all that is there.
All that is coded in that transaction.
Nonce is not in the transaction. Nonce is in the block. Transactions don't have nonce. What transactions have is the signatures, the addresses and amounts and so on. Okay? So what you are showing here is that whoever has, if this is signed, if I have signed, when I sign it, okay, let me show you this picture. This is a very nice picture. So when you say that output, you have the output, it's an UTXO. I mean, you are creating an UTXO, right? And this can be spent. When you are spending it, you have to show that there exists such a thing that can be spent. That is where you are validating the signature with the, the signature with the, that's why you need the previous input. You see that when you're looking at the transaction,
So basically,
you want the previous input.
when a node, when the transactions are grouped and it is sent to a node when a node collects it. So first of all, he has to validate all the transactions.
Yes.
And so this code runs for each transaction.
Yes, exactly. The script runs for every transaction.
Node minds and then it's
Yes.
completed, right?
Yes. So yeah, I will, so SegWit transactions, they have, I can't find it, but each of this, so dupe would have like this value 02, then hash 160 would again have an opcode, so that's where you know that this is the script that is being run. So I can't find that list of SegWit scripts. This is a normal script. In the normal script, you would see that every opcode, every word would have an opcode associated with it, which can tell you that what operation to perform. And you will have several of this type. Op verify, for example, this dupe. There's one dupe, but this is not the one that we are looking at. Yeah, and then there are some bitwise operations. There's some arithmetic, equal, add, sub. These are simple operations. And then, for example, 160, op 160, this something like, hash 160, this would have an opcode, for example. So all these would have opcodes. So similarly, this signature, check signature that you have, that also has a code. So everything has a code that helps you to execute that piece of script. I know everyone is lost at this point. But yeah, I think best would be to take some examples, go through, take random, transactions, look at the structure, try to find these, find this. So first of all, check it is a witness or non-witness. Non-witness means these older ones, these are non-witness. These are not SegWit. So you will get the opcode straight away from here. And then there are witness. There are SegWit transactions, which have another list of opcodes that somehow I'm not able to find at this time. And they would have scripts like this. And you can see them in the piece of, in that transaction code itself, which will be much easier for you to see, individually what it looks like. Okay, for example, will we go back to this one? Yeah. So 02. Yeah, I'm not too sure about this. But how do you figure out where it is?
Why does it have two pieces of code? Does it have two inputs?
Yeah, two inputs. So this is the first input, that is the second input. So these are two inputs and one output. That essentially tells you that it is like two input, one output. And it gives you the input, all that information about the inputs also. Just because the input essentially means that it is an unspent transaction that you are using for this transaction. So this is something that you really have to, that must exist before, and that information is given in that input. Okay, maybe a little bit more digging on this as homework for Friday. Okay. Yeah. So as of now, this is something that we do with the transaction information. Okay. So yeah.
Looking at this website, and I can see the nonce values are in the power of 9. And we know in 1 second about 10 to the power 8 operations run on a computer. So this should all done in almost 10 seconds if one nonce is in the power of 9.
What is the nonce in the power of?
Like nonce here.
1 billion.
It has almost digits of 10 to the power 9. So it should have all have been in it should have mined in almost 10 seconds. Why does it take 10 or on average 10 minutes to do this? Because if you run off and loop, you can do it in 10 seconds. So why do we need 10 minutes on average to do this work?
So your question is, okay, there's a question. Okay, there's a question. This is a very interesting question. So the question is, you have the nonce, which is a 9-digit nonce. Okay, so 9-digit nonce. So essentially, you are doing 2 to the power of 9, you know, you're running that hash to almost equal to 2 to the power of 9 times. Why is it then, which can be done very quickly, why then do you have a 10 minutes thing? Can anyone answer? Say it loud. Question.
So the nonce value I observed in the recent blocks, they are in the power of 9, like 5 into 10 to the power 9 or 4 into 10 to the power 9. And we know on average it takes 10 minutes to mine a block.
Yeah, 10 to the power of 9. What is 2 to the power of something?
2 into 10 to the power 9, but it has some factor x into 10 to the power 9. So almost in the power, in the range.
2 to the power of?
2 into 10 to the power 9.
10 to the power of 9.
But almost in this, we are not going to 10 to the power 10.
Okay. 10 to the power of, almost 2 to the power of 12-ish.
Yes.
Yeah.
So we know in a second on a computer we run almost 10 to the power 8 operations.
Yeah.
So this should have been done in quite a few seconds. So why is it taking on average 10 minutes to do one mining process? To mine one block.
Why? Anyone has answer? Huh? So you are doing 2 to the power of 12 operations approximately. So your question is, why is it taking 10 minutes? Why is it taking 10 minutes? Why is it taking 10 minutes?
We also said the multiplication, the caching function takes milliseconds. So it shouldn't be so long.
Why? So the question is, like, if you have so many numbers and you are starting with say 1, you are just increasing the value of nonce and you are checking for 2 to the power of 12 nonces. So, and each of these,
It is 2 to the power 30.
huh?
It is 2 to the power 30 almost.
Yeah, so 9, 2 to the power of not 12, 2 to the power of 3, yeah.
10.
Yeah, so yeah, to the power of, yeah, so 2, 3, yeah, yeah. So how many minutes would it take?
And we know 10 to the power 8 operations run
Yeah.
in a second.
Yeah, 10 to the power of 8, 10 to the power of 8. So 10 to the power of 8 means how much would this be? 10 to the power of 9. So your question is, if I am taking per second, so I will just take maybe 10 seconds. Why is it taking 10 minutes? Any answer?
So only the operations it is performing in 10 minutes. Only the operations it is performing in the 10 minutes.
Because validation does not take a long
No, validation does not take a long time. So the hash it is computing around 10 to the power of 10 times, right? That's what you are saying.
And because if it would have been 13 or 14 digits, it would have been understandable of taking that much time. I cannot open loop in my computer. It cannot.
I have one question. What is the relation between the nonce size and the mining size, mining time?
No, the thing is that, he's assuming that, you are not.
Why are we using nonce actually?
Oh, okay. The nonce is.
Then automatically.
Yeah. So
it is just to avoid repeat. Right?
yeah. So the nonce is essentially added because you can't it's you cannot.
Repaid.
Huh?
You use the same token again to pay something, right?
No.
Over the transaction, right?
No. It's not about the transaction.
Used once, number used once, and you have to use proof of work to.
Exactly. So I'm saying this.
Proof of work algorithm you have to run to calculate that nonce, no?
No.
To check it's valid or not.
So
None says we use cryptocurrency.
no, not for that. Not for that. So when in the block,
Okay.
there's a nonce field. So the thing is that your hash value should be less than some difficulty level. Hash of the block should be less than some difficulty level, right? For this, everything is fixed, but there is one randomness, and then this is what you can check. So the question is that if I have some randomness, how is that value, this particular value?
Right. The puzzle we are solving. Right?
Yes. Yes. Okay, so let's.
So there can be many permutation combinations also, right?
Yeah.
So you have to have this factorial 10 to the power 9.
Pardon?
Factorial 10 to the power 9, right? It is used.
Which one?
Transaction 0.006.
It's a 10 to the power 9, right? None size.
Non-size, yes.
So
Non-size.
It can be permutation also, right?
Permutation of what?
The 9-digit number. None.
No.
No?
It's a value. So it's a number. What is that number? What was the digits?
This is the nonce value, right? For the latest block, the most latest block that was added. This is the nonce value, and you have to hash then, and it is less than this difficulty, right? So it is in the order of 9. And we know in coding that we understand how.
Okay, I'll check because I had not looked very closely at the nonce. I will check and I will let you know. Okay, that's good observation. You are observing many things now. So you have a lot more questions. That's a good thing. So you are thinking. Okay, so we'll see. I did not see the nonce, so I'll just think what it could be.
10 to the power of 9, each computing will take 0.0006 seconds. That's why we take 10 minutes. We just do the
Which one?
mathematical calculation.
Which one?
He said the computational randomness value is 10 power 9, right? What is the 10 power 9, ma'am? What he represent the 10 power 9?
Nonce.
Nonce.
Randomness.
Yes.
Okay.
Okay, so we'll take this later. I'll have a look into what that nonce is, how the nonce is essentially changed. We can take this. Okay, so this is how things look like for the transactions. Okay. Yeah, so basically I would suggest that if you really want to go deeper into the transaction, then you have to match with whatever these opcodes look like and see what script is being run. Now Bitcoin has Bitcoin is very restrictive. It cannot run loops or things like that, which Ethereum can. And that's why the smart contracts that we write for various application is using Ethereum, because Bitcoin's functionality is very limited. All the applications that ma'am was talking about in the afternoon and yesterday, these require a lot of programmatically validating things. So those are not possible with this restrictive script. However, it is good enough for doing transactions. Okay, so next what we will do, let me look into the next part, and this is preparing for so this is all about the Bitcoin. Now we'll look into Ethereum, and with Ethereum I'll just, for the moment, I will simply show you how Ethereum looks like and Ethereum data structure looks like, and then we will, tomorrow when we are exploring scalability. This is very useful. Why we need scalability, how we can scale. So these are useful things to have. So let me show you how the transactions look like, not the Ethereum structure looks like. So here, this is a block. So the block has many parts. You have a parent, the state proof, a receipt try, and so on. So Bitcoin's model is very different. It's not a UTXO model. So Bitcoin has Bitcoin has an account model. So what it says is that for every account, there are a few things that I have to keep. So for every account, so account has some fields. So account address, then account value. This also has a nonce, which means how many times the account has transacted. Okay, so all accounts in the network would have this information. And this is for the externally owned account, but there are also accounts which are contract accounts. So for every contract, you have an account. So yesterday, when you were deploying the contract, you were given an account, account address, So every contract also has this account. So this is a contract account. And this is a externally owned account, Okay, so now for every account, you maintain information about all these accounts in an account trie. You would see an account storage trie. Now what does this account storage trie have? Okay, this contract also had a code hash. So it essentially takes the contract and also keeps the hash of that code. Now every account is kept in this account storage trie. This is a Merkle-Patricia trie. This is a Merkle-Patricia trie. So you see over here, this is forget about this part. Look at this. This is a Merkle-Patricia trie. It is looking like a Merkle trie, but this is actually a Merkle-Patricia trie. So Merkle-Patricia trie is similar to Merkle trie, but it has a little bit more. It's a little bit different. So we will look into Merkle-Patricia trie tomorrow. But imagine that it is similar. So you have these sort of things. Oh, I think I have it in the next slide, maybe. I'll talk about the Merkle-Patricia trie, but this is how the Merkle-Patricia trie looks like. Can you see from the back? Okay, maybe I'll just, let me press this. Okay, so in this Merkle-Patricia trie, at this point, just imagine one thing, that all the information about the accounts are kept in the leaf, and it's similar to a Merkle tree where the root, the intermediate nodes are not keeping any information. So the intermediate roots are essentially help you to figure out how you are going to organize this information. And if you have, how many of you have read tries in data structure? Yeah, tries. Okay, so it's a form of a trie. The only important thing over here is that it is also an authenticated data structure. Essentially, it also has a hash along with the trie. Now, this Merkle-Patricia trie keeps this information about the world state. It keeps on the leaf node are these account information. So these are all account information. So for example, the value is a value, then there are other fields as well. The main point over here is that this is your world state trie, and you keep the hash of the world state trie as a state root. Now when an account when a transaction takes place, or all the blocks have transacted, the account information of all the corresponding blocks will change, right? So between two blocks, so this is for every block. So this every block you have a state trie, world state trie. Now, some of the accounts will change, some of the accounts will not change. But between two blocks, you would have a different world state trie. And the root is only kept on the blockchain. There's also a receipt trie and a transaction trie.
And the whole data structure is not present, only the root hash is there.
Present in the header. So this is a header. This is a block header. The block header keeps the state root. All this information is present in the blockchain itself. Yeah, whole data structure. The transaction trie is a trie that you have seen before. So this is like again the same thing. It is the same as in Bitcoin. It is all the transactions are hashed together in a Merkle tree, and they have a coding which is called an RLP encoding, and it's again the root is kept in the block. But all this is part of the on-chain data. And there's a receipt trie which keeps information of the receipt addresses and so on. Most important of this is the world state trie, because it keeps account information of all the accounts in the blockchain, and it keeps changing. And it forms a large part of the Ethereum data. So that's actually very heavy. It makes it very heavy. Transaction information is not much. Transaction information is very little. However, this account state information is very much. Now, these are the uncle blocks. So in Bitcoin, if a block is abundant, it is completely set out. I mean, it's not kept anywhere. In Ethereum, there's a concept of an uncle block, which means that these were kind of orphaned block, but they are still included. They are still there. So these are the, some of the uncle blocks. Say, for example, there are 5 uncle blocks and there would be 5 headers. And then these are the main transaction within the body of the transaction, within that blockchain. So this is something that we have seen again. So these are the transactions similar to the Bitcoin transactions. So this is how the Ethereum data structure looks like.
Uncle blocks again.
Uncle blocks are like blocks which are similar to orphaned blocks. Orphaned blocks means, suppose someone has created a block, but this is an invalid block, so it should be thrown off. In Bitcoin throws it off, and Ethereum keeps it as an uncle block.
So basically all miners are creating a block, and the block that approves gets the header, and all those not approved. Right?
Yeah. So those are uncle blocks. Now this is, when I'm talking about the state trie, this is how a state trie looks like. However, there's one more thing. Some of these contracts, these would have some storage values. Say, for example, I want to store a string in the contract, or I want to store a value of a particular variable in the block. So all these information is also called an account storage trie. So this is, if this is a contract, if this is a smart contract, so you would have all these account information, say all the storage information. So it could be a value, it could be a string, it could be NFT address, or it could be anything. So all these are stored in the account storage trie. And this account storage trie information, the hash of this is again put in the account information over here. So essentially, you can think of this world state trie to be the information about all the state tries. So essentially, it looks like this. If you think, that there's a world state trie, so this is a Merkle-Patricia trie, but I'm just drawing it as a Merkle trie. So this is kept in the block. And within this, there is another Merkle tree, because that is kept here if it is a contract. Okay, so this is how the Ethereum data structure looks like, and it is important to note that since this information is very, very large, it's a very big bottleneck for Ethereum, and that's where tomorrow when I talk about scaling strategies, I'm going to say how Ethereum deals with it, deals with this large amount of storage in the blockchain, and we will see how alternatively you can store this information and do transactions in a different way that will not generate so much data on the network, on the blockchain network. Yes.
In Ethereum, light folks are not there because you said for each epoch we elect a leader, and that publishes a block and it validates. So there can be multiple blocks in processing in one epoch. So there can be no forking in the main line of Ethereum. So there are no pending blocks that could be approved.
What is?
No pending blocks, so there is no double spending problem here, right? Because we only
Yeah, so double spending problem is double spending problem is taken care of.
Light folks in the Ethereum blockchain compared to Bitcoin, because there are no change of permutation in which we are dealing with transaction, because only one leader is publishing the transaction block.
Yeah, but at the time of publishing, you could have something, only that there could be two things that have been proposed, but then one is validated, but temporarily there could be forks, but within that checkpoint that I said, after that there's nothing, no forks.
You said in Ethereum we choose the heaviest chain.
Yeah, heaviest chain.
So in which context are we saying the heaviest chain? Like the heaviest amount of data we have in the chain?
That's a very interesting question. So the one that I showed with the heaviest chain, that was in the proof of work based.
And this is proof of
Stake. Yeah. Okay. So, couple of things that I wanted to say is it's something that ma'am talked about in the afternoon, and those are related to the light clients and the actual full nodes, because the light clients are the nodes where, so as I said in the previous example, all this data is to be kept in the blockchain, right? So a full node keeps all this data. So it keeps the transaction state, trade try, transaction try, everything. So that makes it extremely big. So 1.5 approximately. However, Ethereum stores only the 128 blocks in the full node. The rest of it is stored in the archival node. There are certain light nodes which store much less information. They don't store the whole state try, but they will keep only the state information. So those are the light nodes, but light nodes have to sync or get information from the full nodes in order to validate things in the past that has happened in the past. So this is an important point to make note of. And the archival nodes are the nodes, as we were talking before, like if it is like long ago, then you have to have clients which have the archival data in order to figure out what the data was looking like. So that's something to remember, because some of you really want to run these clients and see. I think it's a good idea to run these clients and see how they look like. So there are light clients that you can really see. It's not very heavy. You can see how things work using the light clients, but with full storage it might be more expensive. Okay. There's another thing that I wanted to tell you is that we talked about these transactions, and this is the last thing for today. So we talked about these transactions being, this transaction from A, B to some output C, right? So it looks like a very systematic way of looking at things. However, if you try to analyze this sort of data, you would see patterns emerging from this information. So what does it mean, patterns emerging? These can be thought of as a graph. Okay, so graph where the nodes are my addresses, and if an account is making a transaction to another account, then there is an edge. And then by looking at these transaction graph, you can get meaningful information of the transaction in the that is happening in the network. And this essentially violates the it can lead to interesting challenges, because we typically believe that Bitcoin is or cryptocurrencies are anonymous, but these are pseudo-anonymous, as as ma'am said in the afternoon. However, to make them anonymous, there are different strategies that are taken, and one of them is to use a mixer. What does a mixer do? A mixer is a third-party service. It takes transaction, mixes up together, and gives the output. So when you are looking into Bitcoin transactions, for example, sometimes you will see transactions with many inputs and many outputs. These are possibly mixer inputs and outputs. And a mixer, you have to, like mixers, there are other issues with mixers. If you are using a mixer, it means that it is a third-party service. So the third-party service will have all the linkability, will be able to link transactions together. But there are ways and means to counter that as well. So if you are looking into transaction data, just don't panic if you see, oh my gosh, there's so many transactions which are in the input and so many in the output. What does it mean? So it is possibly a mixer which can take maybe 20 transactions, 40 transactions, 100 transactions, and mix them up together just to make it a little bit unlinkable.
Ma'am, if we do not know the node, we have the address of the node, but we do not know where the node is or who the identity of the person, why do we have to use a mixer? And for example, if we still have, for example, after a long time, there's a drug deal in a market and we get a connected component in a graph. But how do we still get the information of which node is present where, and why does it affect, and why do we have to use a mixer? Because we do not know the identity of the node, right?
Yeah, we don't know the identity of the node, but we could. Maybe that node, if you just hit back in the past, you can see that it has exchanged, you used a cryptocurrency exchange.
Banning of that node.
Pardon?
To prevent the banning of that node.
Banning.
Restrict it from spending and transacting.
Yeah. So essentially, for example, I want to trace back. What can I do? What I can, if I did not have a mixer, I would be able to link things together, and I could possibly trace, we think that we'll not be able to trace, but even little clues can help us. Say, for example, it had transacted with a exchange at some point of time. So we might be knowing its address and so on. So there was this, the Silk Route, the person, he was, that whole, it was discovered by using this traceability or traceability analysis of this, of the transactions, because at that point of time there were no mixers and they were able to find. Okay, so yeah, so this essentially shows that there are connections between different transactions, and you can do a graph analytics to show this information. Yeah, so there's also some work that we had done, trying to figure out how ransomware attacks work, and that was also doing that analysis, graph analysis of this sort of a thing. Okay, so we will stop here at this time, and maybe we can take it up tomorrow from where we are leaving with the Ethereum data structure. Okay, thank you very much. And think about the problems that we discussed